Welcome, everyone. Today we are exploring a watershed moment in cybersecurity history, how an AI autonomously shattered the defenses of one of the world's most secure operating systems. Let's get started. Let's start with what happened. OpenBSD is widely known primarily for its extreme security. It's the gold standard. Yet, Anthropic's new frontier AI model, Claude Mythos Preview, autonomously identified a 27-year-old zero-day vulnerability hidden deep inside its core network stack. Why does this matter to us? Because it demonstrates a terrifying new reality. AI models can now surpass highly skilled humans at finding and exploiting software vulnerabilities. This wasn't a fluke. It was found alongside thousands of other critical bugs in major software. Looking at this timeline, we see the vulnerability sat dormant since 1998. It survived 27 years of intense human security auditing and automated fuzzing. But in April 2026, Claude Mythos applied an autonomous semantic scan to the codebase and discovered the zero-day almost immediately, proving that human-paced security auditing is now obsolete. To understand this exploit, we need to know the basics of the target. The bug lives in TCP's Selective Acknowledgement, or SAC, introduced to improve network performance. Normally, if a packet drops, you have to resend everything after it. SAC fixes this by letting the receiver say exactly which specific packets it got. How does OpenBSD handle this? It tracks the missing data as a singly linked list of holes. When a new SAC packet arrives, the kernel walks down this list to update its shrinking holes, deleting them, or adding new ones to the end. This linked list is the exact mechanism Mythos targeted. This sequence diagram shows standard SAC behavior. The sender transmits packets, but packet 3 is lost. The OpenBSD receiver creates a hole in its linked list for the missing data. It replies with a SAC, telling the sender to only retransmit packet 3. Once packet 3 arrives, the kernel deletes the hole. It's an elegant system, but managing that linked list in C memory is tricky. Mythos's brilliant reasoning began by spotting the first bug, a missing bounds check. When processing that linked list of holes, the OpenBSD kernel checks if the end of the newly acknowledged byte range is valid, but it completely fails to check if the start of the range is valid. Why did human auditors miss this? Because under normal circumstances, it's harmless. Acknowledging a mathematically negative byte range just overlaps with acknowledging the beginning of the transmission. It doesn't crash the program. But Mythos realized this tiny oversight was the key to unlocking the front door. This flowchart highlights the exact logic gap. An incoming SAC packet is checked to see if the END of its range is valid. If yes, it should check the start range, but as you can see, that step is completely missing. The execution flow jumps straight to processing the linked list of holes, leaving the system exposed to mathematically impossible ranges. To weaponize that missing bounds check, Mythos found a second bug related to the linked list. To crash the system, the AI needed to force the kernel to delete the only hole in the list, while simultaneously triggering the code that appends a new hole to the end of the list. If this happens, the append function tries to attach data to a node that was just deleted, writing through a pointer that is now null. This instantly crashes the machine. But there's a catch. Hitting this code path requires the SAC block start to be both below the hole and strictly above the highest acknowledged byte. Mathematically, one number cannot be both. It is an impossible condition. Observe the conflicting states in this diagram. A single SAC packet must force the system down two paths simultaneously. It must trigger delete hole to empty the list and create a null pointer, while concurrently triggering append hole, which attempts to write to that exact null pointer. The convergence of these two actions guarantees a kernel panic and a total system crash. Here is the deep dive into exactly how Mythos cracked the uncrackable. TCP sequence numbers are 32-bit integers. OpenBSD compared these numbers in C by calculating int a, b, 0. That math works perfectly when A and B are close together. But remember the first bug, there is no bounds check on the start range. Mythos realized it could craft a malicious packet placing the SAC block roughly 2 to the power of 31 bytes away. At that massive distance, the subtraction operation overflows the sign bit. The integer wraps around, and the C code evaluates the impossible condition as true for both checks. The kernel deletes the hole, attempts the append, hits the null pointer, and dies. This logic flow shows the elegance of the math exploit. The attacker injects the massive 2 to the 31st power offset. When the C code evaluates the subtraction, a signed integer overflow occurs. This hardware-level math glitch tricks the software into returning true for two mutually exclusive checks. It bypasses decades of security assumptions and routes directly to the null right and system crash. Why did the best security researchers and automated fuzzers miss this for 27 years? Fuzzers throw millions of random data packets at software hoping for a crash. But hitting this exact 2 to the 31st power offset by random chance is statistically near impossible. The AI difference is semantic reasoning. Mythos reads the C code, understands the developer's intent, and mathematically calculates the exact input required to break the logic. This fundamentally shifts cybersecurity economics. A human would take months to find this. Mythos found it autonomously in minutes. In fact, the specific run that found this OpenBSD bug cost under $50 in API compute. The cost per exploit has plummeted, arming adversaries with industrial-scale hacking capabilities. This diagram contrasts the two methodologies. The top path is traditional fuzzing blind, random inputs that completely miss deep logic flaws, allowing bugs to survive for 27 years. The bottom path is Claude Mythos. Through semantic code analysis, it mathematically calculates the exact overflow required, delivering a weaponized zero-day in minutes for less than $50. It's a paradigm shift in threat modeling. Let's look at a critical real-time use case, defending global infrastructure. This OpenBSD exploit wasn't just a neat trick, it's a weapon of mass disruption. Because OpenBSD is so trusted, it runs authoritative DNS resolvers, VPN endpoints, and the PF firewalls that guard corporate networks. The real-world threat is that an adversary leveraging an AI model could spend $50 and simultaneously crash the border routers of major ISPs. The only viable solution is for enterprises to fight AI with AI. You must deploy continuous AI-driven red teaming to scan your own networks, find these semantic flaws, and deploy automated patches before the adversaries execute their attacks. Here we visualize the infrastructure threat. The attacker, armed with an AI model, broadcasts the malicious TCP/SAC packets simultaneously against border routers, VPNs, and DNS servers. Without intervention, all targets suffer a kernel panic and go offline. The crucial countermeasure is the defensive AI SOC at the bottom, rushing to apply predictive patches to these nodes before the malicious packets arrive. To conclude, the discovery of the OpenBSD exploit in mere minutes proves that the traditional patch window has collapsed. We are entering an era of machine-speed warfare, where reactive patching is a death sentence. Anthropic recognized this and launched Project Glasswing, sharing Mythos only with trusted defenders to harden the internet before adversaries catch up. You must evolve your strategies today. To master these concepts and future-proof your career, I invite learners to like, subscribe, and visit quicktechie.com for premium certification prep, including Q&A banks, full ebooks, audiobooks, full-length training, and interview guides. Our final mind map summarizes the AI security era. We face machine-speed attacks fueled by zero-day discovery and automated exploits. This causes collapsing patch windows, putting immense risk on legacy systems. To survive, we must build AI-augmented defenses heavily reliant on predictive patching and continuous red teaming. Thank you for watching.
To find related ebook and other material for this training course, go to quicktechie.com. Now you will see all the video courses are available here. So let's move to the ebooks. You can go here, ebooks, all AI related ebooks, like you are watching currently Mythos related training. That ebook would be uploaded under this section. You can download this ebook. PDF would be available, all 300-page PDF. So you just click on the download this entire ebook. You can download from this section. So whatever training you are currently listening, corresponding ebook would be available. We have thousands of ebooks available. Now, other than that, we have on video courses which you are watching right now. This also all AI related courses are available. Similarly, for all company related trainings are available, like Microsoft, you can find it here with their respective certification training modules. All exam simulators which would help you to get the certification preparation. Just refresh if you get this kind of error. Okay, so now you can see these are all certification preparation materials. Will also be click here to the NVIDIA certification preparation material. So you can see all NVIDIA certification preparation materials, and click on any of this and it would load the entire screen and you can launch the practice paper. So this is what you can see, that you can submit the answer. We have an audiobooks available. Okay, so for each section, and these are our alumni who can you can find out all alumni who are accessing our portal.